On the left, we find the derivative of a single variable function by calculating the slope of a simple tangent line. Because we cannot divide by a vector to yield a single number, the multivariable derivative is rebuilt as a geometric transformation, mapping one vector space directly to another. Notice how this 2D coordinate grid behaves as it stretches and rotates. The grid lines remain perfectly parallel, stay evenly spaced, and the central origin never moves. This rigid behavior defines a linear transformation, a mapping that strictly preserves vector addition and scalar multiplication. Within this mapping, certain input vectors might lose their dimension entirely. We call the specific subset of inputs that are flattened into the zero origin point the kernel, or null space, of the transformation. Once the mapping is complete, we look at the resulting state in the codomain. This total set of all possible outputs is the image, or the range. Because linear mappings adhere to such predictable structural rules, they are the ideal tool for approximation. We can use these flat, calculable mappings to approximate chaotic, non-linear surfaces at a specific point. To compute these transformations, we rely on the matrix representation theorem. Watch the standard basis vectors, I and j, move to their new locations. The coordinates of where those specific vectors land dictate the entire transformation, and they form the columns of our matrix. This operation translates a vector from an n-dimensional space into an m-dimensional space. The matrix acts directly on the input vector, mathematically expanding or collapsing the geometry into its new dimension. Matrices translate the abstract concept of geometric mapping into the literal language of calculation. To apply calculus operations to these transformations, we need a definitive way to mathematically measure the topological size of a matrix. This diagram illustrates the solution. Here is a perfect unit circle being transformed by a matrix into an elongated ellipse. We assign the operator norm as the supremum of the magnitude of this transformation applied to all vectors within that unit ball. In geometric terms, this is simply the maximum stretch. The norm is the length of the longest stretched vector produced by the matrix. Let's test this intuition. What is the operator norm of a diagonal matrix with entries 3 and -5? The answer is 5. Even though -5 is the smaller coordinate value, the operator norm measures absolute magnitude. The transformation stretches the geometry to a length of 5 along the y-axis, making the magnitude of that stretch exactly 5. The operator norm is the analytical bridge that gives us a measurable topological distance, allowing us to compute limits on the algebra of matrices. Because we can now measure the distance between any two linear transformations, the set of all such mappings forms its own complete metric space. This allows for the study of complex compositions and inverses. This architecture scales into modern computing. In machine learning, the backpropagation algorithm relies on the Jacobian matrix, which is a linear transformation operating on high-dimensional data. It also extends into differential geometry, where these transformations allow us to define flat, computable tangent spaces on curved manifolds. As shown in this summary, the logic follows 3 parts. Linear mappings preserve vector geometry, matrices compute those mappings, and the operator norm measures their topological size. Mastering these concepts in Rudin provides a rigorous analytical foundation for handling motion, optimization, and continuous change across any number of dimensions.